Hi everyone. Today I am going to discuss uh, about plastic collapse load. First of all, we know that what you mean by load factor, what you mean by collapse load, what you mean by plastic analysis. Okay, when we are calling all these conditions, so the structure is said to be collapse if the entire structure or a part of the structure starts undergoing unlimited deformation. The state at which this condition develops is said to be in a collapse mechanism, and the load carried at this stage, oh, this load is called as a collapse load. Mm. The structure we are considering a whole structure. I am going to consider the frame structures. Okay, so it is in the state of plastic state after the elastic state and after the yield conditions, yield point. The load is applying continuously on this structure. Also, when the load is reaches in the plastic stage or undergoing unlimited deformations. Okay, after the yielding point, the structure is going to or element of the structure is going to unlimited deformations. At this stage, the some conditions is developed that is called as a collapse mechanism, and in this collapse mechanism, load is how the load or what is the load, that load is called as a collapse load. Hence, determining the collapse load of structure, the collapse load of the structure you are going to determine or identify, that is called as a plastic analysis. And one more thing, structures are permitted to carry only a fraction of collapse load is known as a working load. Fraction of collapse load is called as a working load. So we have to know some conditions or differences between or relationship between collapse and working load is as follows. Collapse load, which is equals to, in the sense what, collapse load which is equals to load factor into working load. Okay, working load in the sense what, we know that. Okay, so the structure permitted to carry only a fraction of collapse load. So that is a working load. That working load is having some load factors, that is multiplication of load factor, then we get the collapse load, or collapse load divided by working load is called as a load factor. Okay, then the WC, which is equals to, that is a collapse load, which is equals to Q into working load. Q in the sense load factor, Q in the sense load factor, this is a load factor, and this is W of W in the sense working load. So then load factor in the sense we can identify or rearrange the terms, load factor in the sense collapse load divided by working load. Collapse load divided by working load is called as a load factor. And also factor of safety, in the sense we know that already in the previous studies we get the idea about factor of safety, that is yield stress divided by working stress. Okay, so then the next part, we have to continue related to this. We shall now study the collapse mechanism. To a simply supported beam, I am going to consider with a point load at the center. Okay, so I am going to consider a simply supported member which is subjected to point load at the center of this member. So the load is considered as a collapse load, and center in the sense L by 2. Though these are L by 2, and this point is considered as A and this point is considered as B. Okay, so AB member which is subjected to collapse load at the center of the member. Okay, so maximum bending moment of this structure is we know that from the previous studies or previous subject studies. So this maximum bending moment we can get, that is WL by 4. That W is a collapse load, that is WCL divided by 4 we can consider. On further increase of the load, the yield stress will spread into the inner fibers. Okay, so we are keep on increasing the load. Okay, the yield stress will be spread or keep on moving the undeformation or unlimited deformations. Okay, when the load is further increased and reaches the collapse load, the entire section at C is in the plastic condition. Okay, entire structure is in the plastic condition after yielding conditions or after yield point, after passing the elastic stage, that is in the plastic stage or plastic condition. The plastic hinge is developed at the center section. Okay, some plastic hinges are there. Okay, when we are call it as the plastic hinges. Okay, the plastic hinge in the sense what? Okay, we have to study plastic hinge in the sense. So zone of yielding due to flexure in the structural member. And a plastic hinge is similar to the fractionless hinge in that rotation can occur without any change in the bending moment, right? After this condition at this plastic hinge stresses remains constant. Plastic hinges the stress there is no changes because already it is in the plastic stage, okay, but strain and hence rotations can be increases, okay, because of little bit deformations or elastic stay in the plastic stage. Okay, so however it should be recognized that the moment is represented as MP at plastic hinges rather than 0 at the fractionless hinges. So it will develop in a span first at section subjected to greatest curvature, okay, least radius of gyration we can call it is. So then we have to know about the position of plastic hinges, where we are getting the plastic hinges likely to be formed at point of maximum bending moment in the beam. For example, simply supported member we considered, so where we are getting the maximum bending moment for point load middle acting, the middle is maximum bending moment is occurs at the middle. So this point we can identify that is the plastic hinge is developed at this point. So similarly at the section of sudden change in the geometry, if the changing the geometry of cross section of the member changes, okay, at that point also we can identify the plastic hinges. So the plastic hinges will form, and at the fixed end, okay, so if we are considering the one end is fixed, another one is simply supported or cantilevers. So in this point we are getting the plastic hinges over here. Okay, so at rigid joint in the frame, okay, so rigid joint if we are considering the frame, so this in this this rigid joint is also form the plastic hinges. So intermediate joint of continuous beam, okay, if you are considering the continuous beam, so like this, so this is the exterior support, these two are the exterior support, this one is the intermediate support. In this exterior supports are simply supported, so that's why we are not able to identify or we can say that is a simply supported, so that's why there is no plastic hinges developed in that. So in intermediate support we can identify how the plastic hinges is developed in this point. Okay, at the point of zero shear also plastic hinge will be available. At the material changes point and under point load we can identify the plastic hinges. So then in this condition maximum bending moment for simply supported member WCL divided by 4 we can identify. In the sense next point is plastic moment. So plastic moment in the sense Fy into Zp, okay. From previous study we get the plastic moment in the M is in the sense what the stress into modulus of section, okay. So modulus of section for rectangle we can get so Z in the sense I by Y, okay, I by Y. So for rectangle we can consider this is a I, the rectangular member, so B is the breadth and D is the depth, so BD cube by 12 is our I value, moment of inertia. So I in the sense D by 2, so BD cube by 12 divided by D by 2, D by 2, so then 2 1s are 2 6 are D get cancelled, BD square divided by 6 we can get, so Z is our BD square by 6. So then equating about two equations Zp and plastic moment, M maximum and plastic moment, so one second, after principle of virtual we'll study later. So first we have to study or equating those two conditions. So in the WCL divided by 4 equals to Fy into Zp. So this is a one equation, that is a MP equation, another one is a maximum bending moment equation. So we can equating both the conditions, then by simplifying it we need the collapse load, so WC which is equals to Fy into Zp into 4 divided by L, okay. So this is a one condition. At working load point, this is a collapse load, so at working load point we can consider W instead of taking WC as the central load of the member, so we can consider instead of WC is WW we consider, so WW equals to in the sense WWL divided by 4 we can consider, and same condition, okay, Fy into Z or Zp is considered as a Z. So in the sense working load in the sense it is in the in between the point. So that's why in the plastic section we consider here only then yield conditions we are going to consider. So that's why, so where f is equals to, okay, so then it is a factor of Fy divided by factor of safety. So that is W equals to, or WW working load, okay, in working condition 4 by L into F into Z. So this is a condition. We can consider the load factor, okay, Q, which is equals to, we know that collapse load divided by working load. Okay, in the last slide we get the load factor. So that is collapse load to the working load. So in this, Fy into Zp divided by F into Z. Okay, by comparing these two or equating, we are getting the value of this factor of safety and safe factor, the load factor, which is equals to F into S. How it is F into S? So the safe factor, load factor, which is equals to, we are getting load factor which is equals to F into S. How it is? So then in next video we can get virtual work done and how to analyze the collapse load. Okay, in the next video we can study